Hello, this lecture is called Bernoulli equations, and we're going to review, work in detail, an example about solving differential equations with an initial condition that a differential equation that's considered a Bernoulli type of equation. So first, we'd like to remember the form that if you look at this differential equation, here, of course, we are assuming that y is a function of x, right? And so here we have one first derivative of y, and here the term y appears there. Notice that if n were going to be equal to 0, then here we would have y to the 0, which is 1, and then that equation would become linear. But as it stands, this equation, when n is not 0, this equation is not linear, okay, as it is. So when n is 0, this equation there is not linear. And another thing to remember to point out is that n could be an integer, okay, could be an integer number, but in general, n could be considered a real number. It doesn't necessarily have to be an integer, but in some cases, the example we're going to discuss in detail is an example in which n is an integer. So here we have the exercise. So we have x, y prime plus y times quantity x plus 1 plus x times y to a power there, and then we have an initial condition. So one thing that what we need to do first is to make sure that this equation takes the form of what we call Bernoulli, a differential equation of this type, Bernoulli. So as you see how this general form of Bernoulli has the first derivative appears there with a coefficient, if you will, of 1 times y prime. So let's work, let's rearrange terms here, okay? And so we're going to work with the differential equation first. So if we take that differential equation and divide by x, okay, so here's the original differential equation, x, y prime plus y times x plus 1. So let's suppose that x is not 0, otherwise we couldn't do what we're doing here. So we divide by x every term of this equation, and this would give us y prime plus, I'm going to write actually the y as a second term here, something multiplying y plus y to the 5, and then on the right side of the equal sign we have 0. And what we're left with here is 1 plus 1 over x. Okay, so if we compare, maybe we need an extra step, we could move this term to the right side of the equation. So this means that now we can write the equation in this form. We have a power we have power of y here, and that is being multiplied by -1, right? And so now this is in comparison to this general form, right? So you have 1 times y prime, we have an expression in x multiplying y, and then an expression multiplying a power of y. In this case, that expression that we're calling q, in this case here, we're going to consider this to be q, and this other expression here is what we're calling p of x, right? So in this case, q is constant, but it now has that form, and then we notice that here the power is what we're calling n, and n equals 5. So the method is to set a new variable, substitution, which is defined in terms of a new power of the form 1 minus n. In this case, it would be 1 minus 5, which is y raised to the power -4. So now we'd like to write an expression for the first derivative of v, and maybe this is a good time to observe that we're defining v as a function of y, specifically a power of y, but we were assuming that y is itself a function of x. So when we define this new variable v, really what we're saying is that v is a function of x. And so it makes sense to then differentiate v with respect to x, and we can write, we can write dv dx, or we can write something like v prime, but this prime means that we're differentiating with respect to x. So therefore, when we compute the derivative of v with respect to x, we're differentiating y to the power -4. Using the power rule of differentiation, we have -4 times y to the -5 times the derivative of y with respect to x. So this is implicit differentiation. And then we can solve for the derivative of y in terms of the derivative of this new variable. And we can basically solve from the previous equation, solve for the derivative of y. So I'm going to divide in both sides by -4 y to the -5. So here we divide by -4 y to the -5. Then what we obtain on the left hand side is -1/4 times y to the 5 times the derivative of v. So let's remember the original problem. I'm gonna call this problem number 1 here, like equation 1 or expression 1, and I write that 1 in square brackets there. So we have x times y prime plus this other stuff. We're gonna go back to the original problem and substitute for y prime. Okay, we're doing a substitution. We define a new variable v, and now let's substitute to obtain an expression in terms of v and derivatives of v. Okay, but before doing the substitution, let's remember that we had actually worked with the expression 1, and we have modified that expression to make it clear that that equation 1, it actually is equivalent to an equation that's considered Bernoulli. So let me call that Bernoulli equation number 2, and then let's substitute y prime with the expression we obtained for the derivative of v, in terms of the derivative of v. So in other words, we're gonna substitute y prime with this expression, -1/4 y to the 5 and the derivative of v, and we have this, right? So we now have this expression. This is the new version of that equation 2, and well, let's do a couple of extra steps. For example, let's multiply this expression by -4. We multiply by -4 everywhere in both sides of this equation, right? And that would give us that would take care of basically canceling that 1/4, right? So we'd be left with y to the 5, the derivative of v, -4 times that expression times 5 plus 4 times y to the 5. And so the next thing that we can do is to divide or multiply by y to the 5th, or multiply by y to the -5. So we multiply by y to the -5 in every term of both sides of these equations, and that would lead, right? This implies that we have derivative of v. So we have derivative of v -4 times quantity 1 plus 1/x times y to the -4 equals 4. But let's remember that our definition of this new variable, okay, let's remember that v is exactly defined as the power of y raised to the -4. So we can rewrite this expression here. So we have derivative of v -4 times this expression times v equals 4. So this is 1 plus 1/x. So at this step, it's important to note that now this differential equation in v is linear. So I'm going to call this expression 3, or equation 3, and we say 3 is, we know that 3 is linear in terms of v and its derivative, its first derivative, okay? So because of this linearity, we can proceed using the technique of integrating factor. So let's remember that the general form of such equations that are linear, for where equations that where you use that technique of the integrating factor, the general form reads something like this. I'm using here a letter that looks like a P, but it's not P. It's the Greek letter rho. Okay, and then the key is to compute the integrating factor. Okay, and which is defined as the exponential of the integral, okay, of this expression, which is a coefficient of that. So this would be the integral of rho. So in other words, we're always interested on that coefficient of, in this case, this new variable v, okay? And so I'm kind of making the distinction that that coefficient, so that you don't get confused, we started by saying that the original form of the Bernoulli equations is a form that involves an expression p of x and q of x, okay? But once we have done the substitution into the new variable v, we still obtain a coefficient there multiplying the new variable, but that coefficient, that expression, is not necessarily p of the original problem. So it's I just want you to be aware that sometimes you'll read some literature, and so in any case, that's what we're heading towards. We're going to compute the exponential of the integral of that coefficient. In other words, we're interested on the integral of this, and we would like to exponentiate such integral. So first, let's compute the exponential of the integral of this, and let's make use of the initial conditions. So we're gonna set the limits of integration for this between 1 from 1 to x. There is, well, some calculus here in between, and so we would obtain, after doing some calculus there, so e to the minus 4x times e to the 4 divided by x to the 4th. So computing the exponential of the negative of the previous argument, things are very similar, but now we obtain the negative of the argument of the exponential, which means e to the positive 4x minus 4, and then we have x to the power 4. In the previous expression, we had x to the negative 4. Here we have x to the power 4. So using that technique of solving linear equations by the method of integrating factor, then we can solve, remember, our linear equation is here, right? Is this expression number 3? So we can find the solution of number 3 using that technique, and we find that v is equal to x4 exponential of this multiplying an expression that is defined as 1 plus, okay, and that 1 comes out of initial conditions, plus an integral with limits 1 to x, and the argument of this integral is given in some local variable of integration here, for example, t to the minus 4 times an exponential. So what is left to do is to basically substitute, okay, and substitute. And we remember that v is defined as y to the minus 4. So v is defined y to the minus 4. We set that expression equals to y to the minus 4. And then from here, what we have to do is to solve for y, because we are ultimately interested in the solution of the original exercise, which was in terms of y and x. But what you notice here is that it's not possible to obtain a solution in closed form. We have to leave that definite integral